Japan recently made a significant mark on space exploration history, but its achievement extends beyond simply joining an exclusive group. While it became the fifth nation to successfully land a craft on the Moon, following the United States, Russia, India, and China, the mission from JAXA was defined by a far more ambitious goal. It achieved a landing of such extraordinary precision it could be compared to firing a single skin cell from London to Cairo and having it strike a specific grain of rice. This staggering level of engineering ambition captured global attention leading up to the mission. After the touchdown, however, headlines on Earth began to focus on a different aspect of the mission. Nicknamed the Moon Sniper for its remarkable accuracy, the lander's primary objective was to demonstrate this new capability for pinpoint landings. Consequently, the small spacecraft was not engineered to withstand the brutal environment of a lunar night. Yet, in a turn of events that has puzzled scientists, the resilient craft has now survived 3. It has repeatedly awakened to transmit valuable data and imagery from the lunar surface, all while resting in an inverted position. The spacecraft, officially the Smart Lander for Investigating Moon, or SLIM, is a compact and lightweight vehicle about the size of a passenger car. Its core scientific objective is to study the makeup of olivine rocks located near the Scioli crater, a site approximately 200 miles south of the Sea of Tranquility, where Neil Armstrong took his historic first steps. This landing zone sits on material ejected from the nearby crater, offering researchers a unique chance to examine pristine lunar rock from beneath the surface without the need for drilling. Through the analysis of these rocks, JAXA aims to gain deeper insights into the Moon's origins, its internal structure, and its formation. SLIM also carried 2 very small lunar excursion vehicles, LEV-1 and LEV-2, which were designed to be deployed from the main lander to collect their own independent data and photographs. Beyond its scientific pursuits, SLIM serves as a critical showcase for the latest advancements in engineering and mission operations. Its purpose was to prove a small explorer could execute highly accurate lunar landings. A success would accelerate the study of the Moon and other celestial bodies by enabling a lighter, more precise exploration system capable of landing in hazardous, rocky terrain too challenging for larger landers. To fully grasp the significance of this achievement, some historical perspective is useful. It is a sobering fact that only about 43% of all lunar landing attempts have been successful. Past missions to the Moon were constrained by significant limitations in landing accuracy, due largely to the technology of the era and the challenging lunar environment. For instance, the Soviet Union required a dozen attempts before its Lunar 9 probe finally made a soft landing. In a similar vein, NASA's Ranger series had 6 failures before it achieved its objective. The Moon's lack of atmosphere means that descending craft must depend entirely on engine thrust to control their descent, which greatly complicates the ability to make fine trajectory adjustments during the final landing phase. The lander must reach the surface at a velocity near 0 to prevent any damage to its sensitive instruments. Every Apollo mission touched down perilously close to potential hazards, like rocks, craters, or steep slopes that could have led to catastrophic failure, and they had very limited capacity for making real-time course corrections. The Apollo landings were also confined to the Moon's near side, close to its equator, and under nearly perfect lighting conditions to maximize safety. The trade-off for this caution, however, was that NASA was repeatedly sending missions to the same general area, which meant that direct surface exploration was restricted to this one specific region. If a spacecraft could be developed with the ability to land within a hyper-precise target zone, it could be sent to investigate virtually any location of interest. Scientists would be empowered to conduct targeted studies of diverse rock formations and soil compositions without depending on rovers to travel great distances. This capability significantly reduces mission complexity and expense, while creating new opportunities to explore previously unreachable lunar regions. The Moon Sniper mission cost $120 million. For comparison, the 4 lunar rovers built for the Apollo 15, 16, and 17 missions cost $38 million to develop back in 1972, which translates to approximately $286 million today. More recent robotic explorers, such as the rovers for India's Chandrayaan-2 and China's Chang'e 4, cost around $141 million and $180 million, respectively. This is precisely the kind of progress researchers have been working toward. The area of uncertainty for a spacecraft's touchdown point on an astronomical body is defined by what is known as a landing footprint, or a landing ellipse. In 1969, the targeting ellipse for Apollo 11 measured a vast 18.5 kilometers by 4.5 kilometers. Fast forwarding to 2013, China's Chang'e 3 mission was launched with a landing ellipse of 6 kilometers by 6 kilometers. Then, in January 2024, the JAXA lander made Japan the 5th country to land on the Moon by achieving something extraordinary. It came to rest just 55 meters from the center of its 100-meter by 100-meter target ellipse, a designated zone that is an astonishing 8,325 times smaller than the one targeted by Apollo 11. The technology that enabled this remarkable precision is a vision-based navigation system, which JAXA refers to as its smart eyes. By continuously capturing images of the lunar surface during its descent, the spacecraft could determine its own location in real time. It compared the incoming visuals to detailed orbital maps stored in its computer. Maps created using data from other lunar missions, including NASA's LRO, India's Chandrayaan-2, and Japan's Selene orbiter. These positions were then matched to a broad map encompassing its location to determine the exact landing site. By processing these images instantly, Moon Sniper was able to adjust its trajectory on the fly, allowing it to navigate to its target with unparalleled accuracy. Weighing a mere 200 kilograms without its propellant, a successful SLIM landing would demonstrate that small, lightweight spacecraft can accomplish complex lunar exploration missions. However, the landing did not exactly go as planned. While JAXA managed to place the craft on target, it toppled over in the final moments. After such a precise approach, what caused this grave malfunction? On the 6th of September 2023, JAXA launched SLIM on its course for the Moon. The spacecraft arrived in orbit on Christmas Day 2023 and eventually approached for landing on January 18, 2024. As Japan watched on intently, the approach was live-streamed. One mission team member reportedly described the deceleration to landing as what was expected to be a breathless and numbing 20 minutes of terror. During its descent toward the lunar surface, one of SLIM's 2 main engine nozzles inexplicably came loose just 50 meters above the ground. The resulting off-center thrust induced a sideways motion, a drift the craft attempted to correct with its smaller thrusters, but the effort was not enough. The incredible thing is that SLIM was able to. The primary task for the SLIM lander was to identify any irregularities during its final approach and navigate to a safe touchdown point, thereby averting a crash. However, what transpired was revealed in images from a pair of small, autonomous probes that the craft released just before landing. These pictures showed that the main box-shaped vehicle had tipped over, coming to rest on its nose on the lunar surface. This unfortunate orientation meant its solar panels were aimed away from the sun, instead of facing upward as planned. Without access to sunlight to recharge, the craft's operational life was severely limited by its onboard battery, and a complete shutdown was inevitable. Soon after its arrival, SLIM used its dwindling power reserves to send back a composite image of its landing site. With only 12% of its energy remaining, the JAXA team made the strategic decision to power the lander down, preserving a sliver of hope for a potential recovery once the sun's angle in the sky shifted. Remarkably, just 10 days later, on January 29th, that is exactly what happened. For 2 brief days, Slim was able to power on, drawing energy from the sun, which had since moved to a more favorable position. This moment of elation for the JAXA team was short-lived, however, as they knew the lunar night was approaching, an event that would almost certainly spell the end for the revolutionary little spacecraft. Lunar nights present a formidable challenge for all missions to the moon. The conditions are absolutely brutal, and it is not uncommon for lunar craft to fail to survive them. For instance, the Odysseus lander, the first U.S. craft to reach the moon in 50 years, did not awaken after experiencing a lunar night. Much like Slim, it had malfunctioned on its approach and landed on its side in early 2024. Despite being put into a hibernation mode for 3 weeks, it never powered on again. The moon lacks a substantial atmosphere, which means there is nothing to stabilize its surface temperature. During a lunar day, when the moon's surface is facing the sun, temperatures can soar to 121 degrees Celsius. Conversely, during a lunar night, the surface is plunged into total darkness, and temperatures drop to an average of minus 180 degrees Celsius. This is an extraordinary thermal shock for a small lander to endure. What's more, days and nights on the moon are far longer than the 12-hour cycles on Earth. They each last for 14 days. This means a fortnight of searing heat is followed by a fortnight of complete, freezing darkness. Slim was not designed to withstand a lunar night. So on January 31st, the mission team placed it into a hibernation state for the next 14 days. It was not expected to survive, but the hopeful crew decided they would attempt to establish contact after the sun rose again, just in case. On February 26th, JAXA tried to re-establish contact with Slim, holding few expectations of success. The team's total shock and elation were palpable when Slim responded. Their miracle moon sniper had survived its first lunar night and began transmitting pictures back to Earth. The story becomes even more incredible. After 2 weeks of collecting data and images during its second lunar day, JAXA once again set Slim to hibernate. Surviving one lunar night is no small feat. No one expected Slim to survive a second, but somehow it did. On March 21st, JAXA confirmed they had received more communication from Slim following its second lunar night. The pattern continued in late April, when even more pictures were sent back from the lunar surface after its third lunar night. Slim had totally defied the odds, maintaining its functionality through intense levels of heat and cold that could destroy most electronics not specifically designed for these conditions. Somehow, Slim still managed to send back data and images following 3 lunar nights. These images of the surrounding moon rocks will help researchers better understand lunar geology. In one image, Slim took a close-up photo of a moon rock nicknamed Toy Poodle using a special multi-band camera. Despite some blurriness, geologists can use this to distinguish between the different materials that make up the rock, which offers clues as to how the moon formed. Following the 4th lunar night, JAXA attempted once again to re-establish communication with Slim. However, as of May 27th, they have been unable to confirm successful communication with the moon sniper. Despite all its heroic efforts, it is likely it has fallen silent for good. Still, JAXA's first lunar touchdown is a breakthrough in interplanetary travel. Demonstrating the feasibility of such pinpoint landings opens the door to many other possibilities. One key area of interest to scientists is the South Pole Aitken Basin, where the moon's mantle is suspected to have once been exposed on the surface. NASA is also planning a return to the moon in 2026 with the launch of their Artemis missions. Pinpoint touchdowns like the one executed by Moon Sniper may be vital in helping us get to water ice lying in permanently shadowed regions, which until now have been inaccessible. The Moon Sniper stands as a testament to all the progress and innovation we have achieved since the last lunar era of the late 60 and early 70s. As both public and private interest in revisiting the moon continues to grow, missions like Moon Sniper give us a glimpse into what the second lunar era might have in store. If one were superstitious, one might advise caution when naming space missions. When Russia named its first mission to the moon in 47 years, it was originally given the designation Lunar Globe, which translates to lunar sphere. This name, however, troubled Lev Zeleny, the scientific director of the Space Research Institute of the Russian Academy of Sciences. The word glob was too similar to a different Russian word, grob, meaning coffin. Zeleny changed the name of the mission to Lunar 25, intending to call back to the earlier Soviet lunar missions, which were the last time Russian spacecraft successfully landed on the moon. But perhaps it was too late, and something of that original name lingered, because we now know that Lunar Coffin was a much more apt name for the ill-omened Lunar 25. While we often look at NASA or ESA missions, Russia's space program has historically been quite the powerhouse. Back when Russia was part of the USSR, it was the Soviet Union's launching of Sputnik 1, the first artificial satellite, that triggered the space race in 1957, and for a time, the Soviet space program went from strength to strength. It was the Soviet Union that put the first man into space, and the first woman, the first multi-person crew, and the first dog. Their rockets escaped the Earth-Moon system first, impacted the moon first, orbited the moon first, and took photos of the far side of the moon first. Soviet cosmonauts also performed the first spacewalk, and the USSR launched the first space station, establishing a dominant position in the eyes of many. While the Soviet Union gave the impression it was decisively winning the space race, the reality behind this facade was far less stable. The USSR's program experienced the first fatality during a space mission when cosmonaut Vladimir Komarov's capsule parachute failed upon re-entry. Furthermore, the only 3 individuals to have ever perished in the vacuum of space were a Soviet crew that had been visiting the world's very first space station. Soviet launches were often fraught with malfunctions, but the nation was determined to project an image of success to the world, especially when measured against its American rival. To maintain this appearance, the USSR simply concealed its unsuccessful lunar missions, often claiming that any rocket failing to leave Earth's atmosphere was never intended for a lunar journey in the first place. The truth was that only around 34% of Soviet moon missions were successful, a figure that stands in sharp contrast to America's 60% success rate on similar missions. After the United States landed the first humans on the moon in 1969, a crowning achievement that effectively ended the initial contest, both superpowers appeared to lose their intense focus on lunar objectives. By the mid-1970s, their space programs had shifted toward other pursuits, and no Soviet cosmonaut ever walked on the lunar surface. The USSR eventually abandoned all plans for a crewed landing, deeming the project excessively expensive and, perhaps more critically, seeing little value in arriving second. However, with the arrival of the new millennium and following the 1991 dissolution of the Soviet Union, global fascination with the moon was powerfully rekindled. Scientists began to view the moon as an essential stepping stone for future human expeditions to Mars. Its surface held abundant resources, including newly confirmed deposits of water ice, which could be processed into rocket fuel, breathable air, and drinking water. The moon's low gravity also made it an ideal staging point. These resources soon captured the interest of commercial enterprises for their economic potential, while various nations contemplated establishing permanent lunar bases as a profitable venture. Of course, a vast amount of scientific work remains, attracting researchers eager to better understand the moon's formation and its governing cycles. Russia's historic adversary, the United States, moved to revitalize its own space initiatives, launching the Constellation program in 2005 with the stated goal of returning to the moon. This time, however, other countries were joining the effort. India, which had not participated in the original race, initiated its Chandrayaan program for lunar exploration in 2000. Governments worldwide came to believe that the advantages of this second push to the moon were so significant that any nation not involved would risk falling behind. The chairman of Israel's space agency, Krishnaswamy Kasturirangan, captured this sentiment by stating that the issue was not whether nations could afford to go, but whether they could afford not to. Russia had no intention of being excluded and was keen to embrace the Soviet legacy of space exploration. In fact, it had anticipated its competitors, with Russian scientists Mikhail Marov and Eric Galimov presenting proposals for a new lunar mission to the restructured space agency, Roscosmos, as early as the mid-1992s. Their Lunar Globe mission received approval and was originally conceived as a multi-part endeavor, featuring a penetrator for seismic analysis, a lander, and an orbiter. The project, however, initially lacked sufficient political backing. It suffered from budget reductions following the 1998 Russian financial crisis, during which the ruble's value plummeted and was consistently hampered by delays that forced it to be postponed. Eventually, the penetrator and orbiter components were eliminated, and the mission was redesigned around a solitary lander to improve its economic feasibility. Russia aimed to be a major international force in space, but was unwilling to allocate a massive portion of its budget to the effort. In 2005, Russia's investment in its space industry was just 20 billion rubles, or roughly $700 million US, compared to the $15.6 billion spent by the USA. One strategy to overcome this financial constraint was international collaboration. Russia first attempted to partner with India on the Chandrayaan-2 mission in 2007, under a plan where Lunar 25 would serve as the mission's lander, flying alongside an Indian orbiter. Ultimately, this lower level of spending proved detrimental, as Russian scientists could not get the lander's technology ready for the original 2013 launch deadline. India eventually moved on from the partnership, completing Chandrayaan-2 independently, which left Russia to attempt a solo landing with Lunar 25. Although India's Chandrayaan-2 lander ultimately crashed, the nation was determined to try again with Chandrayaan-3. This sequence of events transformed Russia and India from collaborators into direct competitors. Both nations were targeting the lunar South Pole, where Chandrayaan-2 and other missions had spectroscopically confirmed the presence of water ice. Lunar 25 and Chandrayaan-3 were now in a race to become the first mission to successfully touch down in this region and potentially make direct contact with that ice. Russia, however, soon confronted a new and formidable challenge: the 2022 invasion of Ukraine. In response, Western nations imposed sweeping sanctions that were not only economically damaging, but also included a crucial ban on the trade of advanced computer chips and electronic components. These sanctions were designed to hinder Russia's ability to produce high-precision ballistic missiles for military use, but they also directly impacted its lunar ambitions. European scientists began terminating their collaborations with Roscosmos, and in a deeply interconnected world, where Russia had relied on trade for many of its sophisticated components, it was now forced to proceed entirely on its own. India completed Chandrayaan-3 and launched it on the 14th of July 2023. The mission, as detailed in a prior video, employed a trajectory that was highly fuel-efficient but also slow, requiring over a month to reach the moon. India projected a landing date of August 23. This timeline presented an opportunity for Russia. If it could act quickly, it could launch its own lander on a shorter, more fuel-intensive path, using the powerful Soyuz 2-1B rocket, and arrive first. By this point, the Lunar 25 mission had already been delayed from 2021 to 2022, and then again to 2023. In a stroke of misfortune for Russia, its BIB navigation sensor failed quality control tests. This was a significant problem, because the sensor depended on a computer chip that was normally sourced from the West, a chip Russia could no longer acquire due to the sanctions. Consequently, Russian scientists had to engineer a new system, the BIUSL, from scratch. With this new component developed and integrated, Lunar 25 was finally cleared for launch on the 11th of August 2023, carrying 8 Russian scientific instruments, including advanced laser mass spectrometers. Lunar 25's payload was extensive, with infrared spectrometers, cameras for imaging the lunar surface, and a device to measure dust and micrometeors. Its ambitious objective was to operate on the Moon for a full year, surviving the profound cold of lunar night and the harsh solar radiation of lunar day. The potential for significant science was clear. The Soyuz rocket carrying the probe was powerful enough to deliver it to the lunar surface by August 21st, 2 crucial days before India's lander was scheduled to arrive. Russia seemed positioned to win this modern race to the Moon. Lunar 25 launched successfully from the Vostochny Cosmodrome on August 11, 2023, entering lunar orbit on August 16th. It began its work, transmitting photographs of the Moon's surface, including an image of the Zeeman crater. Initial reports were positive. All systems functioned normally, and communications were strong. Russian scientists then began final preparations for the landing itself. The Moon's south pole is home to treacherous terrain, and the scientists wanted to avoid a rough touchdown which could potentially harm Lunar 25. But then, something went wrong. On August 19th, Lunar 25 lost contact with Earth. No longer guided remotely, the probe attempted its pre-planned maneuver to shift from a circular orbit into a descent path. A critical failure occurred. The BIUSL navigation device, a Russian component that replaced one which hadn't passed quality control tests, sent bad information to the ship's onboard control unit. As a result, its thrusters fired for 127 seconds instead of the intended 84. This prolonged burn pushed Lunar 25 into an ever steeper descent. On the 20th of August, the probe plunged toward the lunar surface at a pace too fast to stop. Roscosmos scientists could do nothing but look on as the lander hurtled into the terrain, traveling faster and faster. Although no external cameras witnessed the impact, it's easy to imagine the grim result of acceleration under gravity that turned Lunar 25 back into a lunar coffin. Its lunar mission had not lasted a year, but only a few days. Later, NASA's Lunar Reconnaissance Orbiter did a flyby, taking an image of the site of the craft's final resting place. Lunar 25 had impacted hard, creating a crater about 10 meters in diameter. Russia had attempted to show the world that it was still a great power in space exploration. However, Lunar 25 had been mired by pressures and challenges. Western sanctions had indirectly sabotaged it. The Russian replacement part was not precise enough or hardy enough to survive the high radiation environment of space. Russia's attempt to beat its rival India had also created problems for itself. The arrival date being 2 days before India's is reminiscent of a similar time when the Soviet Union's Lunar 15 mission crashed into the Moon, only a few hundred miles from and on the same day as Apollo 11's landing. Lunar 15 had been tasked with collecting moon rocks, the same as the astronauts of Apollo 11, although it was unmanned. If America's mission had failed, it would have been a point of pride to the Soviet Union that Lunar 15 had managed to steal America's thunder. This was political point scoring. The Soviet Union didn't just want to get to the Moon, it wanted to get there first. Inevitably, when you're racing to beat someone else, you take less time making sure everything works as well as it needs to, and so you run a greater risk of failure. Ultimately, just like with Lunar 15, Russia's Lunar 25 had the opposite effect that its country's leadership intended. Instead of showing Russia's superiority in space exploration, it showed the downsides of isolationism and rivalry over collaboration. Had Russia still worked with institutes like ESA, sharing in technological advances, perhaps it would be boasting a success right now. In many respects, it's a tragedy. Perhaps this can one day change, as the future of mankind seems pointed towards the stars. If we are to thrive out there, it will be because we as a world work together. The tragic fate of the Lunar 25 mission can and should be a learning experience, not just an embarrassing footnote in history, but only if the right lessons are drawn from it. Pride is not always a good thing. Rivalry can leave us isolated when we don't need to be, and can prevent us from thinking things through. Although it's unlikely, it would certainly be nice if our efforts to prove our superiority to each other could finally be put to rest, buried in a frozen coffin on the lunar surface. The Moon, Earth's natural satellite, orbits approximately 384,000 kilometers away, a celestial object that scientists have studied for thousands of years, using its regular motions to mark the passage of time in calendars. Its dependable rhythms helped ancient civilizations to track when to plant crops, and its waxing and waning phases cemented the Moon's place deep in the heart of symbol and tradition. It's a wonder, a necessity, and a curse. While the Moon's desolate beauty has captured the vision of poets, it also brings desolation. There is one lunar rhythm that is not helpful to us, a 19-year cycle that brings unexpected floods and ruin. NASA scientists are worried that in the middle of the 2030 seconds, it is about to hit its hardest yet. For ecosystems that are adapted to it in the right way, this won't be a problem. But how adapted are we? I'm Alex Mullen, and this is Astronomy. Today we explore the innocently named lunar nodal cycle, and why a better understanding of the Moon's fluctuating behavior is needed to protect ourselves from its dangers. Much like the Sun, the Moon is an inescapable part of life on Earth. The Moon has an immense impact on our planet. You likely have already heard how its cycles influence our wildlife, affect our climate, and create tides. We tend to imagine that the Moon and the Earth's gravities cause them to circle each other in a relatively stable, synchronized harmony. But as is so often the case, nature is not as simple as we imagine it. Instead, every 18.6 years, the Moon's orbit undergoes a subtle revolution, a shift in its alignment between us and our Sun that causes high tides to grow even higher, tipping us over the edge into dangerous flood territory. Let's delve into what this subtle revolution is. Its name is the lunar nodal cycle, or the precession of lunar nodes. This complex name refers to a specific feature of the Moon's orbit of the Earth. You likely know that every 29.5 days, the Moon orbits the Earth. However, this orbit is not flat. To be more specific, there is a 5-degree inclination. The Moon does not orbit Earth on the same flat plane that Earth follows in its journey around the Sunday. Instead, its path is slightly tilted, meaning for half of every month, the Moon travels just above this ecliptic plane, and for the other half, it dips just below. This orbital geometry creates two distinct crossover points, or nodes, where the Moon's path intersects Earth's, an ascending node and a descending node. What is particularly significant is that these nodes are not stationary. They slowly rotate around our planet, completing one full revolution over a cycle lasting 6 years. And it is this gradual precession that sets the stage for a powerful tidal phenomenon. To appreciate why, it is helpful to revisit the fundamental mechanics of our planet's tides. The Moon's gravitational pull exerts a constant force on Earth's oceans, drawing the water toward it and creating a distinct bulge, or high tide, on the side of the planet closest to it. A second high tide, simultaneously, forms on the opposite side of Earth, though its cause is different. This bulge is a product of centrifugal forces, as the Earth and Moon orbit a common center of gravity. Their interaction can be likened to two dancers spinning together, where the larger partner is also pulled slightly off balance. As Earth is swung around in this cosmic dance, the water on its far side is effectively flung outward, creating the second tidal bulge. The Sun also plays a substantial role in this process, though a lesser one. Despite its immense mass, which would otherwise create a far greater pull, its vast distance from Earth reduces its tidal influence to about 1/3 of the Moon's. When the Sun and Moon are aligned in the sky, their gravitational forces combine, producing exceptionally high tides known as spring tides, which happen 6 to 8 times a year. When they are not aligned, their pulls partially offset one another, leading to more moderate tidal ranges called neap tides. The influence of the lunar nodes on this gravitational tug-of-war is profound. During spring tides, the unified pull of the Sun and Moon already creates the highest tidal conditions and the greatest risk of coastal flooding. However, this alignment is never more perfect than when it occurs at one of the lunar nodes. Throughout the rest of the 9.3-year phases of the cycle, the two celestial bodies are not pulling in precisely the same direction, resulting in more temperate tides. But when a spring tide coincides with a nodal crossing, the conditions become far more serious, dramatically elevating the risk of floods. The last time this powerful alignment took place was in September 2015, prompting both the United Kingdom and the United States to issue major flood warnings. While some minor flooding did occur that month, the true damage was inflicted a couple of months later when the amplified tides combined with severe weather. In the US, South Carolina experienced flash flooding in October that caused extensive property damage and necessitated rescues by emergency services. Then, at the end of December 2015, the UK was struck by some of the most severe floods in a century, as the power of Storm Desmond merged with the high tides to cause an estimated £1.3 billion in damages. While these events can be highly destructive, this historical pattern alone does not fully capture NASA's concern for the upcoming alignment in the mid-2030 seconds. An additional element is now at play, amplifying the regular rhythm of this rising flood risk beyond what has been seen in human history. The particular danger this time lies in the convergence of this predictable celestial cycle. With a global system already under considerable stress, even more so than it was in 2015 because of steadily rising sea levels driven by climate change. A new study, led by the NASA Sea Level Change Science Team, projects that this confluence of factors will likely lead to a dramatic increase in flooding events. The report predicts that when the next node aligns with the Sun in the mid-2030 seconds, almost all mainland coastlines of the United States, along with Hawaii and Guam, will experience a huge leap in the number of floods. Some forecasts suggest this nodal alignment could cause as much as 4 times the amount of flooding from one decade to the next, which would damage critical infrastructure and reshape coastlines around the globe. This means human life will inevitably be affected, with these floods impacting shelter, supplies of clean water, and the electrical grid. There is also the increased risk of outbreaks of waterborne diseases like hepatitis A and cholera. Furthermore, receding floodwaters can create stagnant pools where mosquitoes gather, potentially spreading other diseases such as malaria. These physical threats have cascading economic consequences. Such natural events can make coastal life unaffordable, with the increased cost of insurance on homes, or even an inability to find insurance at all, which could trigger a reduction in asset value throughout a community. Consequently, this lunar nodal cycle will likely damage the quality of life in coastal communities, where infrastructure may not be rebuilt or adapted to this recurring force of nature. The impact extends beyond human settlements into the natural world. Ilya Rashin, a visiting professor at Rutgers University, analyzed how the peak of this lunar wobble, where high tides are at their highest, can drown coastal salt marshes. These marshes are critical habitats for a range of species, particularly invertebrates, and these floods can cause them to drown. This, in turn, means that other species like fish and seabirds who rely on invertebrates for their survival also suffer. The effect ripples outward, as salt marshes support a multitude of marine life, which includes 75% of all fishery species. This means the lunar wobble disrupts the food chains of both humans and animals, causing disturbances to their natural habitats and impacting their populations. While much of this seems concerning, it is interesting to note that not all ecosystems on the planet are negatively affected by this cycle of flooding and high tides. Ecologist Neil Saintillan of Macquarie University analyzed how the lunar nodal cycle heavily impacts the expansion and contraction of mangrove canopy cover over most of the Australian continent. The analysis showed that the peaks of the lunar nodal cycle coincided with the densest cover of the mangrove canopy. It revealed that when the lunar wobble is in its minimum phase, it causes mangrove ecosystems to become very dry, which leads to thinner canopy cover. Yet, when the lunar wobble is at its maximum phase, mangrove cover increases. This is a significant positive effect, as mangrove canopies are beneficial to Earth's environment. They are complex ecosystems that fight against climate change, protect wildlife, and shield coastlines from erosion. They can also absorb 4 times as much carbon dioxide as rainforests of the same size. Their growth is therefore vital to the welfare of our planet, so it is not all downside. Still, it is clear that if we do not plan for the coming changes, the consequences could be severe. A significant challenge is looming for coastal environments and the cities within them, which raises the essential question of what can be done. One approach centers on enhancing natural protections. The preservation and active restoration of mangrove forests, for instance, can form a living barrier against flooding, effectively shielding coastal communities from harm. What makes these ecosystems so valuable is their ability to diminish the force of incoming waves. As water moves through the dense network of above-ground roots and branches, both wave height and energy are substantially reduced. This process ultimately prevents powerful waves from scouring the seabed and carrying away sediment. The intricate structure of the mangroves also lessens the energy of the wind, which in turn can inhibit the very formation of waves. Reports indicate that a densely packed mangrove forest can cut a wave's height in half over a distance of just 100 meters. For a sense of scale, a more sparsely populated open forest would require 500 meters to achieve the same effect. It becomes clear that preserving and reforesting these vital habitats, or others with similar properties, can provide a formidable defense against future floods. Another potential path forward involves learning to coexist with flood-prone conditions, choosing to work in harmony with nature instead of fighting against it. A compelling example can be found in the Netherlands, a nation where 1/3 of the land is below sea level and another third is susceptible to flooding. The Dutch have developed an infrastructure that accommodates water and manages the reality of rising seas. A key element of this strategy is the use of polders, which are parcels of land reclaimed from a body of water and situated below the waterline. These areas are typically encircled by an embankment that holds back water from the sea or a river. Polders are engineered with a network of drainage canals and pumps that meticulously manage water levels, channeling any excess back to its source to prevent it from inundating the land. This system protects homes, farms, and industrial sites, making it a widespread feature of the country's landscape. In addition to polders, the Netherlands has also constructed dams and leveraged natural sand dunes, creating a multi-layered approach to staying dry in a naturally swampy region. This demonstrates that by observing nature, we can find ways to live alongside its powerful forces. The sobering reality is that behind its ethereal beauty, our moon possesses an influence that, when combined with other factors, threatens to overwhelm humanity's coastal settlements. Yet, there is also cause for optimism, as knowledge itself is a form of power. By fully understanding the situation we face, we can seek out solutions, drawing from both existing ideas and innovations yet to be conceived. If we hope to navigate what lies ahead, it is imperative that we harness our innate creativity and our drive to adapt and survive, learning to collaborate with our planet rather than working against it. On March 4, 2022, a mysterious rocket booster concluded its journey by impacting the surface of the Moon. This event was closely monitored by the scientific community, which had been tracking the object's silent orbit around Earth since 2015. Upon crashing, it created an unusual double crater that seemed to defy precedent and lacked any immediate explanation. For other observers, the more pressing curiosity was its origin. No nation or entity came forward to claim it. The thought of clandestine government programs or shadowy corporations launching pirate satellites for profit might come to mind, but a deeper look into this object's history reveals a different, and in many ways more troubling, issue. It points toward a rapidly approaching era in which space, rather than being a domain of peaceful exploration, could become a place of danger and conflict. While this is a future one hopes can be avoided, the first step is to understand the current situation overhead. The process of identifying the origins of this rocket booster, designated WE0913A, is actually one of the more straightforward parts of this story. It is highly improbable that it was jettisoned from a secret government mission. While inside knowledge of every nation's classified space programs is not publicly available, the truth is that executing a secret space launch is remarkably difficult. For the last 70 years, ever since the invention of the intercontinental ballistic missile, nations have been deeply invested in monitoring the rocket launches of other countries. During the Cold War, the pervasive fear was a nuclear exchange between America and Russia, making it a matter of national survival for each side to know what the other was doing. This was accomplished with radar and intelligence networks. When Russia launched Sputnik 1957, American intelligence was already aware of it, even if that information wasn't shared with the public. Since then, radar and satellite systems have become so advanced that they can detect launches within minutes. It is now virtually impossible to send a rocket into orbit without being noticed. Rockets are inherently difficult to conceal, and even if a launch went undetected by official systems, the global community of amateur astronomers constantly watches the skies as a hobby. It wouldn't be long before someone spotted an anomaly. A more plausible strategy for a secret mission would be to disguise a spacecraft, perhaps as an ordinary satellite or a piece of discarded space junk, allowing it to drift in plain sight. While this could make more sense for our mystery object, its true origin was likely uncovered through mathematics. As far back as 2015, independent astronomers had been observing the rocket's path. By plotting its course, they were able to calculate its trajectory in reverse, which allowed them to determine which nations it had passed over at different times. This analysis initially led to the belief that it was a component of a SpaceX rocket. However, that theory was later replaced by a far more probable explanation, that the object belonged to the Chinese Chang'e 5T1 mission. The mystery rocket's orbit passed directly over China on the exact day of the Chang'e 5T1 launch, and its trajectory was an exceptionally close match. Further evidence came from the University of Arizona, where students at the Space Domain Awareness Lab used a RAPTORS telescope to conduct a spectroscopic survey of the object. Through careful telescopic analysis of the light reflecting from the object, scientists were able to evaluate its surface paint. This data, when cross-referenced with existing records, pointed to a much stronger correlation with the design of a Chinese rocket than one from SpaceX. The convergence of this evidence led astronomer Jonathan McDowell to state he was 90% certain the mysterious stage belonged to China. However, when confronted by journalists, China issued a denial. A spokesperson for the Foreign Ministry, Wang Wenbin, reported that according to China's own monitoring, the upper stage of the Chang'e 5 mission rocket had re-entered Earth's atmosphere safely and had been completely incinerated. He further asserted that China's aerospace endeavors are always conducted in full compliance with international law. While some astronomers suggest this could be an innocent mistake on China's part, the possibility remains that the statement was deliberately untrue. The reason for such a denial, even against strong evidence, may lie within that final assertion. The prospect of being seen in breach of international law is something China appears keen to avoid, and this situation highlights a growing, worldwide problem. A body of international space law does, in fact, exist, though it is often considered incomplete. This framework is composed of several treaties signed and ratified by various nations over decades. Among them are the Rescue Agreement, which outlines the responsibility of nations to aid astronauts in distress, and the foundational Outer Space Treaty of 1963. This treaty establishes the right of all nations to explore space, holds states accountable for the space-related activities of their citizens, and mandates that celestial bodies like the Moon be used exclusively for peaceful purposes. It is this same agreement that prohibits any nation from placing nuclear weapons in orbit, which is a primary reason why no such orbital platforms exist today. The treaty also makes states liable for any damages they cause in space and requires them to prevent the harmful contamination of celestial bodies. It is likely this last article that China is attempting not to violate. While the impact of the rocket on the Moon likely caused minimal harm, the optics of losing track of a rocket stage that later collides with another world are unfavorable. A more serious concern would be the potential for biological contamination if any terrestrial bacteria survived the journey. The consequences would have been far graver had the object struck a satellite or, in a future scenario, a lunar base, as such an event would place China in clear violation of international law. This incident, however, is more than just a nation attempting to manage its public image. It signals the potential for a new era of conflict. The issue extends beyond the undeniable and worsening problem of space debris. The true source of alarm is that the legal framework governing space is so underdeveloped that the origin of a rocket could be a mystery to begin with. The existing international laws, while noble in their intent, are riddled with ambiguities and loopholes, proving insufficient for ensuring the peaceful exploration of space in the coming years. Consider, for example, the Outer Space Treaty, a cornerstone of space law signed by 117 nations, including the United States, China, and Russia. It explicitly states that outer space is not subject to national appropriation by claim of sovereignty, by use or occupation, or by any other means. Yet, this principle is already being tested. It is difficult to reconcile this language with the ambitions of a growing number of nations to establish permanent bases and conduct mining operations on worlds like the Moon. Establishing a base certainly resembles an act of occupation, and claiming resources seems to be a clear form of appropriation. The Artemis Accords, signed by 23 countries, attempt to navigate this by having signatories legally declare that they are not appropriating the resources they extract. However, other nations have dismissed this as a semantic workaround. Some perceive the American interpretation as a modern version of Britain's 18th century enclosure movement, where land was unilaterally claimed. Depending on the prevailing legal interpretation, any nation that attempts to extract lunar resources could find itself in breach of the treaty, though this risk is clearly not deterring current plans. Furthermore, the Outer Space Treaty's stipulation that space be used for peaceful purposes contains a significant omission. While it bans nuclear weapons and other weapons of mass destruction, it leaves considerable room for the development of conventional armaments. This very idea has been explored. In 2003, 40 years after the treaty was signed, the US Air Force proposed a concept involving two 0-foot-long tungsten rods, nicknamed rods from God, which could be deorbited from space. These projectiles would fall at speeds reaching Mach 10, striking their targets with the force of a small tactical nuclear weapon, but without the radioactive fallout. Their launch would be far harder to detect than a traditional missile. Their travel time would be halved, and they would be nearly impossible to defend against. Ultimately, the idea was shelved due to its exorbitant cost, not because it violated international law. As our global civilization becomes ever more reliant on satellites for commerce, communication, finance, and navigation, these orbital assets are transforming into critical points of national vulnerability. In response, various nations are now developing anti-satellite, or ASAT, missiles to threaten the interests of others and to defend their own. This is a complex escalation with unintuitive dangers. A conflict in space does not behave like one on Earth. When Russia tested an ASAT missile on one of its own defunct satellites, the impact created thousands of pieces of debris, which were scattered into orbit around the planet. Some of these fragments could remain in space for years. If they collide with other satellites or debris, they could trigger a cascading chain reaction of further fragmentation, a phenomenon known as the Kessler syndrome. A widespread conflict of this nature could generate so much debris that it renders low Earth orbit unusable, effectively bringing an end to the age of satellites. An intriguing point of contention in the pursuit of universal access to space involves a treaty promoted by Russia and China known as PAROS, which would prohibit all types of weaponry in orbit. This proposal, however, has been consistently blocked by the United States, which tends to favor a different philosophy, one articulated by President Theodore Roosevelt that endorsed negotiation from a position of strength. An argument could be made that some measure of force in space may be essential for security, which only adds to the intricacy of the issue. To say that a deficit of trust exists between the major global superpowers currently would be a significant understatement. Compounding this, in January 2018, the U.S. Federal Communications Commission denied a company named Swarm permission to launch 4 of its satellites. In response, Swarm simply turned to India and proceeded with the launch anyway, acting without any governmental authorization. This defiance had legal consequences. The FCC eventually imposed a $900,000 fine on the company. The event, however, established a troubling new possibility. As space becomes increasingly accessible to corporations with deep pockets and questionable ethics, it is conceivable that illicit orbital ventures could one day become lucrative. A certain level of enforcement, backed by a credible capacity for force, might prove necessary to safeguard the activities of legitimate scientific and commercial spacefarers. Regrettably, as many observers have pointed out, there seems to be a common preference among nations to champion rules that grant them operational freedom, while simultaneously restricting the actions and ambitions of their rivals. Space, however, urgently needs more comprehensive global oversight. If the world's nations fail to cooperate on a functional framework for continued exploration, the domain risks devolving into a lawless frontier, fraught with potential conflict. In such a scenario, the higher purpose of scientific discovery could be cast aside, which would be a profound loss, especially when international law could be fortified to prevent it with relatively modest effort. The agreements reached thus far do show some promise. A notable example is the Moon Treaty, which designates the lunar environment as the common heritage of mankind, to be utilized exclusively for peaceful activities. Any exploitation of its resources would have to be managed by an international regulatory regime, established through careful consensus. The treaty's major flaw, however, is that very few countries have actually ratified it. Critically, none of the nations with significant launch capabilities, including the United States, Russia, or China, are signatories, rendering the agreement largely symbolic. To date, there has been no accord on what this governing body would entail, or even what the phrase common heritage of mankind truly signifies in practice. If space is to be a secure realm for generations to come, this status quo must evolve. Substantive discussions are needed to forestall future illegal actions and to de-escalate potential arms races in orbit. Any group that sends a rocket into space must be held accountable for tracking it. Ultimately, the leading nations of the world need to find more common ground on these matters. We should not aspire to a future where mysterious rockets crash into the moon. The goal should be a world where the alien beauty of space is cherished, where its hazards and mechanics are understood as purely natural phenomena, and where the moons and planets can be explored with fairness and in peace, rather than becoming objects of conflict and eventual destruction. Perhaps as a species, we need to mature not only in our technological reach, but in our civic wisdom as well. Humanity has always been drawn to new frontiers. Back in the 16th century, after Christopher Columbus first sailed to America, thousands of Europeans embarked on the same perilous, 6-month voyage across treacherous oceans to follow. Upon their arrival, they understood that none of the comforts of European civilization would be there to greet them. They had to cultivate their own food, construct their own shelters, and labor relentlessly simply to stay alive. Many did not survive, perishing either during the crossing or in the difficult years that followed. Yet that did not deter more from coming. The pull of the new frontier was simply too powerful to resist. Now, fast forwarding to the 21st century, another new frontier lies before us. Space. For all its visual splendor, it is the most hostile environment we have ever encountered. Space is a realm of extremes that will burn you, freeze you, and expose you to lethal radiation. Its shifting gravity can either crush you or cause your body to waste away. Not even something as basic as breathable air can be assumed. And yet, this frontier is calling to us. This impulse may reveal something fundamental about human nature that we would endeavor to go to such a desolate place. Perhaps we find meaning in the challenge itself. There is a quality that speaks to certain individuals about venturing into a deadly, hostile territory and creating something warm and safe within it. Or perhaps the motivation is simple curiosity. There is an immense amount to learn about the cosmos that surrounds us. And while studying photographs and analyzing instrument data is valuable, it cannot compare to the experience of witnessing a place, a phenomenon, or a universal wonder firsthand. Moreover, a physical presence unlocks entirely new avenues for science. And so, humanity has set its sights on the other planets of our solar system. It is possible that humans could be walking on Mars as early as 2033, but that journey must start with the Moon. The Artemis mission is designed to return humans to the lunar surface by 2024. In doing so, it will pioneer new technologies and push into uncharted technical territory. The expertise acquired from this undertaking will empower scientists to engineer the spacecraft needed to carry human life out into the wider solar system. It all begins with the Moon, and with Orion 1. I'm Alex Mulan, and you are watching Astrum. Join me today as we look at the first crew-capable spacecraft to travel to the Moon and back in nearly 50 years, following its recent successful splashdown. This mission is poised to open the door to distant planets. So, what exactly did it achieve over the course of its journey of nearly 26 days? The answer offers a fascinating glimpse into just how close we are to having a human on the Moon once more. Orion 1's round-trip voyage to the Moon began at Launch Complex 39B at the Kennedy Space Center in Florida. The atmosphere there was a palpable mix of tension and excitement. This was a mission of great significance, as almost 5 decades had passed since the conclusion of the last space race. But just as before, America is not alone in its ambition to reach the lunar surface. The Chinese National Space Administration landed a rover on the far side of the Moon in 2019, and they have recently engineered a rocket, the Long March 9, that could potentially deliver a human to the Moon in the 2030 seconds. NASA has always been a competitive organization, and it hoped to be the first to return. For that to be possible, the Orion 1 mission needed to proceed flawlessly. The flight plan was designed as a complex retrograde orbit, meaning it would travel in the direction opposite to the Moon's own orbit of Earth. This trajectory would take it on 3 loops around the Moon, 2 of which would be close flybys. This was, however, far more than a simple demonstration. The Orion 1 mission represented a challenge far more intricate than simply navigating a precise course through space. Its core objective was to rigorously test the myriad onboard systems required to sustain human life during such an ambitious undertaking. For future crews, every single component would need to operate flawlessly, as any failure could prove fatal. While this inaugural flight did not carry human astronauts, a milestone reserved for the subsequent Artemis 2 mission, it was not without its occupants. On board was a unique passenger known as Commander Munin Campos. This sophisticated mannequin was internally equipped with a suite of sensitive radiation detectors, its purpose being to meticulously record the levels of cosmic exposure that astronauts would face inside the Orion 1 crew module. The name itself is a thoughtful tribute to Arturo Campos, an electrical engineer whose ingenuity was instrumental in saving the Apollo 13 mission after an oxygen tank explosion. Accompanying Munin Campos were two additional mannequins, each designed to simulate different body types and genders. This was a crucial detail, as later Artemis missions will include female astronauts, and understanding the specific effects of space travel on their physiology is paramount. The very materials of the mannequin's clothing, and of the Orion capsule itself, are part of a larger system designed to shield against this cosmic radiation. A significant concern is that most space agencies consider 50 millisieverts to be the maximum safe radiation dose a person should absorb in 1 year. On the Moon, however, those levels can surge to as high as 380 millisieverts. If NASA is unable to mitigate these exposure rates to more acceptable figures, it would present a grave health hazard to all future lunar explorers. The launch of Orion 1 marked the maiden voyage for both the capsule and its carrier, the Space Launch System. This super heavy-lift rocket is NASA's tallest and most powerful launch vehicle to date, and it currently holds the title of the most powerful rocket in operation globally. At liftoff, it generates an immense 3.8 million kg of thrust, giving it the capability to lift a payload of nearly 70,000 kilograms and propel it toward the Moon. This power was essential for carrying not only Orion 1 but also 10 small CubeSats that NASA would deploy to monitor space conditions for upcoming missions. Following an initial delay, the rocket's engines ignited, powerfully pushing the vehicle up through and beyond Earth's atmosphere before the capsule detached from its launch stages to commence its solitary journey. The first phase of this flight was underway, a 4-day transit to the Moon that NASA intended to use for immediate testing. On the very first day in space, an unusual system was activated. Alexa, the familiar voice assistant, was integrated into the mission as part of the Callisto payload, a technology demonstration developed through a collaboration between Amazon, Cisco, and Lockheed Martin. These companies funded the payload, which is a suite of video conferencing and voice command technologies, to prove how such commercial software could be beneficial to NASA's future endeavors. In a remarkable test, technicians on Earth successfully placed a call to Orion 1 and interacted with Alexa, requesting and receiving information about the spacecraft's telemetry and flight status. It was an intriguing showcase of technology, hinting at a future much like science fiction, where spacecraft operations might one day be controlled primarily by voice. On the third day of its voyage, after performing some course corrections that set it firmly on its lunar trajectory, Orion 1 conducted a detailed visual self-examination. There is a constant, low-level risk from micrometeoroids striking a spacecraft's surface, and capturing these high-resolution images would allow NASA to assess the extent of any damage from this potential cosmic threat. It served as a quiet reminder of the persistent dangers Orion 1 would have to endure. Fortunately, while the data is still being analyzed, it appears that damage from micrometeoroid impacts was minimal on this flight. Throughout those initial days, Orion 1 captured stunning imagery of its home planet, showing Earth shrinking as the spacecraft traveled farther away. it also began to look toward its destination. This first lunar flyby was a critical maneuver, taking Orion 1 over historic sites visited by its predecessors, including Tranquility Base, where Apollo 11 landed, and the locations of the Apollo 12 and Apollo 14 missions. Passing so close to the lunar surface served as an excellent dry run, providing valuable practice for future missions that will need to deliver cargo or personnel. More importantly, this phase demonstrated one of Orion's most vital and repeatedly tested capabilities, its autonomy. For a period of 15 minutes, the immense mass of the Moon would completely block all communications with Earth. Astronaut safety is a paramount concern for NASA, which has invested heavily in developing backup systems for Orion 1. But a key question remained. What would happen if the spacecraft lost contact with Earth and had to navigate entirely on its own? There is no access to Google Maps when traveling at 8,210 kilometers an hour, over 370,000 kilometers from home, although GPS connectivity was tested during the mission as a contingency. Much like ancient mariners navigating the vast oceans, Orion 1 needed its own kind of compass to find its way. Its method for doing so was remarkably similar to that of those early sailors. It navigates by the stars. The spacecraft is equipped with a sophisticated optical navigation camera, engineered to use the positions of stars to track its own position, orientation, and motion through space at any given moment. It achieves this by continuously comparing what it sees with highly detailed, onboard digital star maps. At numerous points during the journey, scientists on the ground tested these systems to ensure their functionality would not be compromised by the harsh environment of space, such as the warping effects of solar heat. Reassuringly, all of these systems performed perfectly. Orion 1 was able to maintain a precise awareness of its location and continued along its correct path. After emerging from this zone of radio silence, the spacecraft passed around to the far side of the Moon and effortlessly re-established contact with Earth. In doing so, it recorded a truly breathtaking sight, an inverse of what we experience on our own world, an Earthrise. Then it was time for still more tests, including a particularly fascinating one known as the sloshing test. Fluid mechanics are notoriously complex. Predicting how liquids like engine fuel will move during acceleration requires advanced computer models even here on Earth. When the complexities of variable gravity are added to the equation, it almost becomes simpler to just go to space and observe the effects directly. NASA was keenly interested in measuring how much, and in what specific ways, the fuel aboard Orion 1 would move under thrust, a phenomenon known as sloshing. This would yield invaluable data that could be used to more accurately predict the amount of thrust needed for Orion 1 to perform various maneuvers in space over the course of the next 2 weeks. During a series of complex and delicate orbital maneuvers, Orion 1's thrusters were put through a series of intense trials. Navigating the fine line between impacting the lunar surface and veering off into deep space requires immense mathematical precision. Any deviation from perfect thruster performance would have jeopardized the mission's fuel reserves, even with the extra supplies carried aboard, but as it turned out, the spacecraft's performance exceeded expectations. The thruster burns were executed with the exactness NASA had anticipated, enabling a second lunar flyby that brought the capsule to within just 130 kilometers of the Moon's surface. Despite the overall success, the journey was not without its challenges. An unexplained communications blackout occurred on the 8th day, leaving the craft silent for 47 minutes. And later, on day 19, a temporary power failure affected the ship's heaters and propulsion subsystems. Mission controllers, however, successfully restored functionality to these critical systems. With the second phase of its journey concluded, only the final and most perilous stage remained: re-entry into Earth's atmosphere. To facilitate this process, the crew module separated from the rest of the spacecraft and began its descent. The module then executed a specialized skipping maneuver, much like a stone skimmed across water, to gently ease its entry and slow its velocity for a more precise landing. The intense friction of re-entry superheated the surrounding air into a state of plasma, creating a predictable but tense period of radio silence. While NASA had anticipated this blackout, ground teams could only wait as the capsule's autonomous systems worked to maintain stability, and its advanced heat-resistant plating shielded the interior from the extreme temperatures. At an altitude of 2,900 meters and moving at more than 200 kilometers per hour, the parachute deployment sequence was initiated. First, 3 small parachutes ejected the bay doors, followed by 2 drogue chutes to begin the deceleration process. And finally, a minute later, the main parachutes unfurled. This carefully orchestrated sequence slowed the capsule's descent to a speed that would be survivable for a human crew. On December 11th, Orion 1 completed its journey with a splashdown in the Pacific Ocean, immediately activating a suite of signal beacons to announce its location. The recovery vessel USS Portland was dispatched to retrieve the capsule. Before bringing it aboard, scientists allowed the craft's outer shell to cool for several hours, a period they also used to conduct additional tests. These evaluations focused on the effects of salt water on various systems and a thorough assessment of the heat shield's performance during its fiery descent. While the full analysis is ongoing, preliminary findings appear very promising. The interior was successfully protected from the 2,800 degrees Celsius re-entry temperatures, and NASA is still analyzing data from the radiation sensors worn by the test mannequins. The wealth of data generated by the Artemis 1 mission will be fundamental to enabling the return of astronauts to other worlds. As humanity's journey to ever more distant frontiers continues, Orion 1 had successfully completed its role in that grand endeavor. This brings to mind the Apollo program, an iconic chapter in the history of human scientific achievement. Even today, some of Apollo's milestones remain unsurpassed, as it stands as the only program to have ever sent human beings beyond low Earth orbit. With renewed international efforts to return to the Moon, aiming for dates as early as 2024, it feels like a fitting moment to revisit humanity's first great leap to our nearest celestial neighbor. What is intriguing is to explore the original motivations for going to the Moon, and to understand what we discovered once we arrived. The program itself was a vast undertaking, involving 12 crewed missions and more than a dozen uncrewed flights. A story filled with technological breakthroughs, immense challenges, triumphs, and tragedies. At the time, NASA's Apollo program was the largest research and development initiative ever undertaken by a nation in peacetime, a distinction it still holds. At its zenith, the effort employed 400,000 people and collaborated with 20,000 different universities and industrial firms, consuming a remarkable 4.4% of the entire U.S. federal budget. When you consider that NASA's budget today is approximately 0.5% of federal spending, it raises a compelling question. Why was there such an intense national focus on reaching this single objective? To find the answer, one must first look to the historical context of the era, which begins with the Cold War. Following World War II, escalating tensions between the world's 2 superpowers, the United States and the Soviet Union, created a global stage where each nation sought to demonstrate its own superiority. This was far more than a simple rivalry. It was a profound ideological conflict where the success of one was viewed by the other as an existential threat to its fundamental way of life. The United States feared that Soviet advancements could signal the end of capitalism and democracy, while the USSR believed that failing to surpass America would mean the demise of the communist ideal. A deep and pervasive suspicion defined the relationship, with both sides determined not to be outdone. It was within this tense atmosphere that on the 4th of October 1957, the Soviet Union launched Sputnik 1, the world's first artificial satellite, sending a wave of alarm across the American public. Weighing 83 kilograms, Sputnik 1 was 8 times larger than any satellite the U.S. had in development, and it circled the globe 1,440 times during its 3 months in orbit. Soviet scientists used its transmissions to gather valuable new information about the density of the upper atmosphere and the properties of the ionosphere. The powerful R-7 rocket that carried Sputnik 1 into space could generate 4 million newtons of thrust, a figure that dwarfed the 670,000 newtons produced by the most capable American rockets of the time. This technological gap was deeply unsettling to the American public for 2 primary reasons. The first being the ever-present threat of nuclear war, which made the knowledge of an adversary's powerful rocket technology a source of profound vulnerability. It was clear that such a rocket could just as easily carry a nuclear payload as a scientific one, a legitimate fear, given that the R-7 was. The advent of Soviet rocketry, particularly designs engineered with a nuclear payload capacity, introduced a profound shift in global power dynamics. Until that point, the United States had been largely insulated from direct attack by its geographical remoteness, but this new technology erased that advantage. Beyond the immediate military threat, a deeper anxiety took hold across America, a fear that the nation was falling behind the Soviet Union in the critical domains of science and technological innovation. Responding to this national sentiment, the yet-to-be-elected John F. Kennedy campaigned for the presidency on a central promise: he would secure American supremacy over the USSR in the arena of space. Once in office, he began to explore how to fulfill this pledge and was reportedly stunned by the immense financial commitment it would demand. However, a pivotal event on April 12, 1961, forced his hand when the Soviet Union achieved another historic milestone, sending the first human into orbit. This prompted President Kennedy to urgently ask his advisors for a grand objective, a challenge that could not only match, but decisively surpass the Soviets' progress. The response arrived just days later, on April 20th of that year. The recommendation was that to truly leapfrog the Soviet Union, which already possessed a significant lead with its powerful R-7 rockets, America needed to pursue a goal that was currently beyond the reach of either superpower. The proposed target was one of monumental scale, conceived to capture the world's imagination. NASA would land a man on the moon. This audacious challenge would necessitate a technological leap of an unprecedented scale. To lift the massive assembly of rockets and modules required for a round-trip lunar mission, American engineers would need to develop engines producing 50 times more force than their existing technology could generate. The mission would also demand a correspondingly massive financial investment. NASA's budget was swiftly approved and expanded. In 1961, the agency was allocated $744 million for its various endeavors, but just a few years later, as the program's requirements escalated, that annual figure swelled to over $5 billion. With this infusion of capital, NASA began a period of rapid expansion. It constructed new launch complexes and state-of-the-art mission control centers, hired a new generation of specialists, and acquired advanced research equipment, including vacuum chambers, capable of simulating the near-perfect void of space. While the agency had been conceptually exploring a crewed lunar mission since early 1960, this new combination of political will and vast resources allowed them to address the problem with urgent seriousness. Several competing mission plans were developed to outline the complex sequence of events. One proposal, known as direct ascent, envisioned a single colossal rocket that would fly directly to the moon, land, and then return to Earth. Another concept, called Earth Orbit Rendezvous, suggested a more modular approach, where up to 15 separate rocket launches would carry individual components of a spacecraft into orbit to be assembled there. Each of these early plans presented significant difficulties. A single, massive rocket for a direct flight would be extraordinarily heavy, as it would need to carry all the fuel required to escape the gravity of both the Earth and the Moon. The sheer lift required for such a vehicle was far beyond what American rocketry could achieve at the time. The second idea, assembling the craft piece by piece in Earth orbit, also had critical drawbacks. While it solved the lift problem by breaking the payload into smaller, lighter segments for each launch, the cost and complexity would be astronomical. Every individual launch would cost hundreds of millions of dollars, and the task of constructing a sophisticated spacecraft in the vacuum of space was an unproven and daunting feat. Ultimately, NASA settled on a third, more elegant strategy that combined the most effective elements of the other concepts. The mission plan, which they named Lunar Orbit Rendezvous, involved a single rocket carrying two primary spacecraft, a capsule-style command module, and a separate landing craft called the Lunar Module would be sent out of Earth's orbit together. Upon reaching the Moon, the two modules would separate. The much smaller and lighter Lunar Module would then descend with astronauts to the lunar surface. After their exploration was complete, it would launch them back up to reconnect with the orbiting command module. Once the crew and any collected samples were safely transferred back, the command module would make the solitary journey home to Earth, concluding with a splashdown in the ocean. While it seemed intricate, this model was calculated to be the most efficient approach in terms of overall mass, thrust requirements, and cost. With this architecture finalized, NASA could move forward with construction and testing. The agency would need to create rockets far larger and more powerful than any built before, put its own astronauts into space, and meticulously test every phase of the intricate journey. The path was set, and the Apollo program had officially begun. The sentiment expressed by Isaac Newton that his vision was enabled by standing on the shoulders of giants applies perfectly to this endeavor. The Apollo program was not a singular achievement that emerged from a vacuum. Its success was entirely dependent on the vital missions that came before and ran concurrently with it. It was built upon the knowledge gained from those earlier efforts, expanded on their technological foundations, and relied on the seasoned expertise of the people who had made them possible. Here at Astrum, I'm Alex Molan, and in our exploration today, we will examine two of those foundational programs, Project Mercury and Project Gemini, to understand how they empowered a young NASA to solve the immense puzzle of putting a human on the Moon. We hope that by the conclusion of this journey, you will feel a part of our community of discovery. NASA itself is a relatively recent institution, established only in 1958 as a direct response to the Soviet Union's launch of the Sputnik satellite a year prior. Yet, it would be inaccurate to suggest that the agency was created entirely from scratch. When President Eisenhower authorized its formation, he did so by consolidating a number of pre-existing government programs and scientific bodies. These included the NACA, or the National Advisory Committee for Aeronautics, the U.S., Army's Ballistic Missile Agency, and the group of German scientists who had developed ballistic missiles for Germany during World War II. Furthermore, the U.S. .2 Air Force had been developing its own Man-in-Space Soonest, or MISS program, which was transferred to the new agency along with some of its facilities. These and other government projects formed the bedrock upon which NASA was built. Among all these combined assets, however, there was no existing capability to place a human into orbit. The program that came closest was NACA's X-15, a rocket-powered airplane that could touch the very edge of the atmosphere. In the early 1,960 seconds, the X-15 set incredible records, flying to an altitude of 105 kilometers and reaching speeds exceeding 6,000 kilometers per hour. A later version of the X-15 would push that boundary even further, surpassing 7,200 kilometers per hour and setting a record for the fastest crewed-powered aircraft that remains unbroken to this day. But while this altitude was above the 100-kilometer Kármán line, the FAI's official definition of the boundary of space, it was still a suborbital flight. To venture beyond the sky, it was understood that the airplane had reached its absolute limit. Something entirely new would have to be conceived to carry a person into Earth orbit and, with time, to the surface of the Moon. This realization led NASA to initiate its very first human spaceflight endeavor, Project Mercury. The mission of Project Mercury was, in essence, an extension of the earlier Man in Space Soonest program, and as its name implied, the primary goal was to successfully launch a man into orbit and ensure his safe return. A critical, unspoken objective was to accomplish this before the Soviet Union. The task was monumental, as riding a rocket into space presented a host of dangers. An astronaut would have to withstand immense gravitational forces and severe vibrations, all while sitting atop what was fundamentally a repurposed ballistic missile, with the constant risk of a catastrophic explosion. Survival also depended on enduring the searing heat of re-entry. Beyond these immediate threats, scientists held concerns about the effects of radiation outside the protective shield of the atmosphere, and even the possibility of micrometeors striking the spacecraft. While some of these fears, like a damaging meteor impact, were found to be statistically negligible, the other risks posed a very tangible threat to human life. The launch vehicles NASA employed for Project Mercury were the Redstone rocket, which was eventually succeeded by the more powerful Atlas rocket. A notable detail is that both of these systems were originally developed as military missiles. The Redstone itself was a direct technological descendant of the German V-2 rocket, a weapon of war. Following the end of the Second World War, the United States brought numerous German scientists to America, tasking them with advancing the nation's weapons and technology programs. Among them was Wernher von Braun, a German scientist who would become a chief engineer at NASA. His expertise proved indispensable in developing the rocket technology not only for Project Mercury, but later for the Apollo missions as well. The flight plan was designed for a launch vehicle to lift a small capsule to an altitude of 161 kilometers, jettisoning spent boosters and other unneeded components during the ascent. The capsule would then enter an orbital path around the Earth, reaching a maximum height of 280 kilometers. After completing its orbits, the pod would fire its own small boosters to begin its descent back into the atmosphere. To survive the immense frictional heating of this phase, which could reach 1,600 degrees Celsius, a specialized heat shield was required. Finally, a sequence of parachutes would deploy to slow the capsule for a gentle landing in the ocean, where it would await retrieval. Success depended on a number of complex systems functioning perfectly. The boosters, for instance, had to be released at precisely the right moment to minimize the vehicle's weight, a sequence that did not always go as planned in early tests. The program was also pioneering the use of new ablative heat shields. Rather than trying to completely deflect thermal energy, these shields were designed to absorb a tremendous amount of heat and then burn away, dissipating that energy as a gas. This carried the excess heat away from the craft, but it was a delicate calculation. If the amount of shield material was underestimated, the craft would be left unprotected and would burn up. To account for potential malfunctions while a person was on board, extensive redundancies were engineered into the rocket systems. A rocket-powered escape vehicle was even integrated into the spacecraft, functioning as a kind of sophisticated ejector seat for the entire capsule. This entire process demanded exhaustive testing before any human mission could be attempted. The very first effort in August 1959 ended in failure. Due to an incorrectly installed power plug, the Mercury Redstone rocket, known as Little Joe, one lifted only about 4 inches from the launch pad before settling back down. Subsequent launches saw a mix of outcomes. Von Braun oversaw a total of 20 tests between 1,959 and 1,961, with most of these flights being uncrewed. A few, however, carried trained monkeys and chimpanzees into space, as von Braun was determined to be absolutely certain of success before entrusting a human life to one of his rockets. While his caution represented excellent scientific practice, it came at a significant cost in the context of the space race. In April 1961, that cost became clear when Russia achieved the goal first. The Soviet Union successfully launched cosmonaut Yuri Gagarin into orbit, making him the first human being in space. Von Braun's first human launch occurred just 1 month later, carrying astronaut Alan Shepard, but this was still only a suborbital flight. From the American perspective, the score was now 2-0 in favor of the Russians, who had launched the first satellite and now the first human into orbit, causing considerable worry in the United States. In the end, Project Mercury would launch 6 human flights, 2 aboard Redstone rockets and 4 on the Atlas. All of these missions were successful, and although the program did not achieve its goal of being the first into space, the lessons learned were invaluable. The project provided an essential foundation of knowledge about launching rockets, enduring the conditions of space, and surviving the perilous journey of re-entry. However, when NASA formally announced the Apollo program in 1960, with its audacious goal of reaching the moon, it became evident that a much greater depth of knowledge would be required. Mercury's final and longest mission had kept an astronaut in space for a day and a half, yet a round trip to the moon was projected to take 8 days. Furthermore, NASA had decided that the most efficient way to land on the moon was to use the lunar orbit rendezvous method. This plan necessitated the mastery of what was perhaps the most complex maneuver in space travel, docking with another object in orbit. This was a feat that had not yet been achieved, even in the relative safety of Earth orbit, let alone in the vicinity of the Moon. The lunar orbit rendezvous concept involved a lunar module separating from a command and service module, descending to the Moon's surface, and later ascending to meet back up with the orbiting command module, which would then carry all the astronauts home. In addition to this, astronauts would need to practice performing spacewalks, in case any external repairs to the spacecraft became necessary during the long transit. Finally, more experience was needed with re-entry techniques, specifically with touching down at a predetermined location on land, though this last objective was ultimately dropped for the Apollo missions. On top of these immense technical hurdles, the Soviet Union remained ahead, and America felt an urgent need to catch up. So, while the Apollo team began the long process of developing its powerful rockets and modules, these other critical challenges were assigned to a dedicated support mission. That mission was given the name Project Gemini, launching 12 missions between 1961 and 1966. Project Gemini was designed to build directly upon the foundations laid by Project Mercury. The Gemini capsule itself was essentially a scaled-up version of the one used on Mercury, now capable of carrying a crew of 2. The rocket selected for the task was a Titan II, another military missile that was adapted for a new purpose of peaceful discovery. Gemini also represented a significant expansion of the technology developed for Project Mercury. The Mercury spacecraft had possessed very little ability to alter its own course once it achieved orbit. If an orbital rendezvous was ever to be possible, this fundamental limitation had to be overcome. To address this, the Gemini spacecraft was equipped with what was called an orbit attitude and maneuvering system, which gave it the ability to change its orbit and orient itself precisely while in space. The craft was also engineered to support a crew for much longer durations. By the time of the Gemini 5 mission, astronauts were able to spend an entire week in orbit. To be certain of their capabilities, later flights extended this time to a full 14 days by Gemini 7, which was 6 days longer than the time required for a complete mission to the Moon and back. While these missions saw a great deal of success, there were also moments of intense danger. Neil Armstrong, for instance, flew on the Gemini 8 mission. The primary objective of his flight was to meet up with and perform the first ever docking with an uncrewed Agena target vehicle that had been launched separately. The initial phase of the mission unfolded without incident, culminating in a successful docking maneuver. Yet, while Neil Armstrong and co-pilot David Scott were still aboard the target vehicle, a dangerous situation began to emerge as their combined spacecraft started to rotate in space. This uncontrolled spin presented a catastrophic risk. A collision during the undocking sequence could inflict fatal damage on their Gemini capsule. What made the problem more severe was the uncertainty of its cause. If a thruster was firing continuously, it would be consuming precious fuel that was absolutely critical for orienting the craft for a safe return to Earth. An incorrect re-entry angle would mean their heat shield could not protect them from the incredible temperatures generated upon hitting the atmosphere. The two astronauts worked rapidly, using an opposing thruster to slow the violent rotation of the connected vehicles. This gave them just enough stability to return to the Gemini craft and perform a narrow, but safe, undocking. It was then they discovered the malfunction originated with one of their own Gemini thrusters. Both crew members were close to blacking out from the ordeal, but they successfully addressed the fault. Armstrong, with immense composure, then used the re-entry thrusters to arrest the capsule's tumble, bringing it back under control with only 30% of his fuel reserves left. This near disaster powerfully reinforced the need for astronauts to perform extravehicular activities, or EVAs. The Gemini program, therefore, also saw missions where crew members practiced working outside their spacecraft. Buzz Aldrin set a notable record for this, conducting a spacewalk that lasted 5 hours and 30 minutes. This endurance test proved that sustained work outside a vehicle was entirely possible, as long as proper rest periods were incorporated. It also gave engineers practical ideas for making such tasks easier, such as installing handholds at strategic points on the craft's exterior. In the end, it was the cumulative work of both the Gemini and Mercury programs that laid the necessary groundwork for the next chapter. Thanks to the discoveries made during these missions, NASA was making substantial progress toward its lunar objectives and was steadily closing the technological gap with the Soviet Union. It would now be up to the Apollo program to take those final steps. The telling of these stories is an endeavor made possible in part by a community of supporters on Patreon. For those who find educational value in these accounts and wish to ensure their continued creation, independent of algorithmic shifts, membership offers a way to contribute directly. Members are able to view the complete video ad-free, receive a credit for their support, and can submit questions to our team. Details for joining are available through the link in the description. From myself and the entire Astrom team, we extend our sincere thanks. Our journey continues in the linked playlist featuring more Astrom content, and we hope to see you again.